Diffraction of light, wave aspect of light. Good morning. We're going to explain a new chapter, that is diffraction of light. When the sun shines on a certain obstacle, a tree for example, the object casts a shadow because light was being stopped by this obstacle, and the shadow has the same shape as the obstacle. As you can see right here, the shadow has the same shape as the obstacle. Now, when light shines on an opening in a box, for example, light forms a bright or a lit region. This bright region has the shape of the opening, be it rectangular or circular, etc., etc. Now, how can we interpret the form of the lit region or the shadowy region? It can be interpreted by the principle of rectilinear propagation of light. The principle states as follows. Light propagates in a straight line in a homogeneous medium. This principle can interpret the shape and dimensions of the shadow or the lit region. Now, as the day approaches noon and the sun moves like this, light rays fall almost vertically and the shadow becomes narrower. And if we decrease the width of the opening, the lit region becomes smaller and smaller in dimensions. The essential question that arises here is, what if the width of the opening was made extremely small? For answering such a question, we're going to conduct an experiment. In this experiment, we are going to use a light source, laser, emitting a narrow divergent beam. We observe a circular spot of small dimensions and a small radius. Now, what if we bring and place in front of the laser beam different rectangular slits of very small dimensions, of widths 0.05 millimeters, 0.1 millimeters, and 0.2 millimeters, and let us observe what happens. Now, let's place in front of the beam a rectangular slit of width 0.05 millimeters. So what do we observe? Here we observe a wide lit spot. So you see, there is the wide lit spot that is surrounded by two lit spots of smaller widths. These two lit spots are separated by a dark region, right here. These lit spots are called bright fringes. The dark regions are called dark fringes. Let's repeat the experiment by using a slit of width 0.1 millimeters. We observe the following figure. In the same manner as before, containing bright and dark fringes. The bright and dark fringes are alternatively placed, with a wide bright fringe being in the center. We call it the central bright fringe. Now, when using the 0.2 millimeter slit, we also observe a similar pattern. Here we are using a circular slit, and you can see concentric fringes. The slit used here has a diameter of 0.4 millimeters. The central spot is much brighter than the surrounding spots. Now let us study the diffraction pattern of a laser beam entering a thin rectangular slit of width A, which is less than 1 millimeters. This slit is placed horizontally, and this is the observation screen. This is the slit that's placed horizontally, and this is the observation screen. When the laser beam enters the slit of width A, we observe the figure here that is formed of a diffraction pattern of a central bright fringe surrounded by bright and dark fringes. When the narrow beam enters the slit, it's spread out from the other side. This doesn't comply with the principle of rectilinear propagation of light. Thus, the diffraction phenomenon contradicts with the principle of rectilinear propagation of light. Returning back to the screen here, the region isn't lit completely, as you can see, but there are points or dark regions. So how can we interpret the formation of such dark regions? And how can we interpret the formation of the bright ones? To interpret the formation of bright and dark fringes, we use Huygens' principle. Huygens' principle says that a wavefront is formed of infinite punctual or point sources that are synchronous and coherent. Each source of this wavefront, which is formed of infinite sources, emits a ray, so that all rays superpose at a certain point M. If this superposition is destructive, the amplitude of the vibrations at M is zero, and therefore the luminous intensity at M is zero. We thus obtain a dark fringe. Whereas if the waves superpose constructively at M, point M will have a maximum vibrational amplitude, and as a result, the luminous intensity will be maximal. This leads to the formation of a bright fringe. The diffraction experiment showed evidence of the wave aspect of light, which considers light as being a wave, to interpret the presence of bright and dark fringes. It also showed a flaw in the principle of rectilinear propagation of light, because the principle of rectilinear propagation of light is incapable of interpreting the phenomenon of diffraction. Here we show the diffraction pattern of the laser beam from a thin wire of diameter 0.1 millimeters. We observe on the screen the diffraction pattern that is similar to that obtained by a rectangular slit of the same thickness as shown previously. In general, diffraction is realized when light encounters an obstacle or slit of width less than 1 millimeters. Studying diffraction by a rectangular slit. When the direction of the slit is vertical, the diffraction pattern is aligned horizontally. Now, when changing the slit's direction to become horizontal, the diffraction pattern becomes vertical. Therefore, and as a conclusion, the direction of the alignment of the fringes is always perpendicular to the direction of the slit. Notice here that the width of the central bright fringe is approximately 1 centimeters, and that the width of any other bright fringe around the central fringe is approximately 0.5 centimeters. That is to say that the width of the central bright fringe is always double than that of any other lateral bright fringe. Let's now place a slit of 0.1 millimeters in width. You can similarly observe that the width of the central fringe here is approximately 2 centimeters, whereas the width of any other bright fringe on either side is approximately 1 centimeters. Thus, again, the width of the central bright fringe is equal to double that of the lateral bright fringes around the central bright fringe. Moreover, if we want to describe the pattern, we observe fringes that are alternating bright and dark, equidistant, perpendicular to the direction of the slit, with the width of the central bright fringe being double that of each of the other bright fringes around it. In this paragraph, we will get to know what the angular abscissa of a dark fringe is. It is used to determine its position. Now, let's take any dark fringe, where we denote by mk the position of the center of this dark fringe. K is the order of the fringe, so it can be the first, the second, the third dark fringe, etc., and so on. The slit must have a width less than 1 millimeters for the diffraction phenomenon to be realized. Theta k will be the angular abscissa that is formed between the ray mk, where I is the center of the slit, and IO, where O is the foot of the perpendicular drawn from I to the observation screen. Now, according to Huygens principle and some difficult mathematics, which we will not cover here, we obtain the following expression of sine theta k, the sine of the angular abscissa of the dark fringe of order k, which is equal to k lambda over a, where lambda is the wavelength of the used light or radiation, and a being the width of the slit, and k being the order of the dark fringe, which is always a non-zero integer. -3, -2, -1, 1, 2, 3, etc. Now, keep in mind that this study is always made for a rectangular slit. Rectangular slit. Now, as an example, to facilitate things, this rectangular slit has a width of 0.2 millimeters. This is the observation screen that is at a distance of d equals 1.5 meters from the slit, and the slit is illuminated by a source of monochromatic light of wavelength lambda equals 630 nanometers. The question is, calculate the angular abscissa of the dark fringes of order 1 and -2. Of order 1 means that k equals to 1, and of order -2 means that k equals to -2. Now let's use the formula. Sine theta k equals to k lambda over a, where theta k is the angular abscissa of the dark fringe of order k. Now for the dark fringe of order 1, k equals to 1. So sine theta 1 equals to 1 lambda over a which is 1 times 630 times 10 to the negative 9, divided by 0.2 times 10 to the negative 3, and the answer will be 0.0315. Now, for small angles, sine theta 1 is extremely small. Then, theta is extremely small as well. And as a result, we can use the approximation of sine theta 1 approximately equals to theta 1. And of course, the angles should be expressed in radians. And therefore, the answer is theta 1 equals to 0.0315 radians. Now, in any example and problem, use the radian in your calculators. Here is an example for demonstrating by calculation why the previous approximation can be used. Let's take these small angles in degrees and their corresponding values in radians. We notice that when using the calculator in radians, sine theta equals 0.1 is approximately 0.1, and the tangent is approximately 0.1 as well. For theta equals 0.05 radians, sine theta equals 0.05, and its tangent is 0.05 as well. For theta equals to 0.15 radians, for example, sine theta equals 0.15, and tangent equals to 0.15. You can always use the following assumption. For theta less than 10 degrees, sine theta approximately equals to tangent theta approximately equals to theta itself in radians. Only use this approximation when the values of theta are in radians. This is an important note. Now, for k equals to negative 2, that corresponds to the dark fringe of order negative 2, sine theta negative 2 equals negative 2 lambda over a, which is negative 2 times 630 times 10 to the negative 9 over 0.2 times 10 to the negative 3. The answer is negative 0.063. And for the same reason, theta negative 2 is approximately equal to negative 0.063 radians. So as you notice that theta can take either a negative or a positive value. That is to say that theta 1 corresponds to the dark fringe of order 1. For example, this is theta 1. This is M1, which is the center of the dark fringe of order 1. And theta negative 2, here it is the angular abscissa of the center of the dark fringe of order negative 2. So this side corresponds to the positive values of theta, while the other one corresponds to the negative values of theta. The question here is, calculate the distance between O and the centers of each of the previous fringes. So we have to determine O, M1, and O, M negative 2. Now think of a way to determine O, M1 knowing theta 1. So you think none other than the trigonometric function, the tangent. In triangle OI M1, we have tangent theta 1 equals to, here's the triangle right at O, tangent to theta 1 equals to OM1 over OI. OM1 over OI. So OM1 equals to OI times tangent theta 1, which is equal to D times Now, using the previous approximation, theta 1 is very small. So tangent theta 1 is approximately equal to theta 1 in radians. And so we get d times theta 1, which is equal to 1.5 times 0.0315. The answer is 0.04725 meters, which is also 47.25 millimeters. Similarly, we can calculate OM negative 2 by using the triangle OIM negative 2. So in triangle OIM negative 2, we can write tangent theta negative 2 equals OM negative 2 over OI. But here the answer should be placed in an absolute value because we're finding a distance. So we get OM negative 2 equals to OI times the absolute value of the tangent theta negative 2, and in the same manner tangent theta is approximately equals to theta in radians, of course. So we get d times the absolute value of theta negative 2, which is equal to 1.5 times the absolute value of negative 0.063, and we get 94.5 millimeters. Now in part C, we have to deduce the angular width and the linear width of the central fringe. To do this, let's first draw a figure. Here's the figure. Here's the observation screen, and this is the central fringe. These are the other bright fringes. This is I. Here's M1. And here is theta 1. The angular width of the central fringe is the angle alpha. This angle is between these two rays that surround the central fringe, or it is between the rays reaching the dark fringes M negative 1 and M1. The central fringe is bounded between the dark fringes of orders 1 and negative 1. So to determine alpha, and by symmetry of the figure, alpha is equal to 2 theta 1, which is equal to 2 times 0.0315. The answer is 0.04725 radians. This is the angular width of the central fringe. Whereas the linear width of the central fringe is this distance L. So L is the distance M1, M negative 1. And here's O. So L from the figure is 2 OM1, which is 2 times 47.25 millimeters, and the answer is 94.5 millimeters. Part D. Calculate the linear width of the first bright fringe. So here is the first bright fringe. And here's the first bright fringe from the other side. So how to determine the linear width of the first bright fringe? Note that the first bright fringe is bounded between the two dark fringes of orders, -1 and -2. So to determine the linear width of the first bright fringe, you have to find the distance m, -1, m, -2. And from the previous part, we found OM1 and OM -2. OM -2 is equal to 94.5 millimeters, and OM -1 as a distance is equal to OM1, which is equal to 47.25 millimeters. And then m -2, m -1 is equal to OM -2 minus OM -1, which is equal to 47.25 millimeters. Here's the linear width L of the first bright fringe from either sides, as you see. If we compare the width of the central fringe L to that of the first bright fringe, you notice that L equals to 2L, and this complies with the experimental observation. In this part, we want to find the general expression of the linear and angular width of the central fringe, given by a rectangular slit. This is the diffraction figure given by a rectangular slit. The screen E is at a distance d from the slit, and let's designate by lambda the wavelength of light. The angular width, like the previous problem, is alpha. So to determine alpha, we use the relation that alpha is always double the angular abscissa of the first dark fringe. And to determine θ1, sine θ1 equals to 1 lambda over a, which is lambda over a. But θ1 is very small. Therefore, sine θ1 is approximately equal to θ1, which is equal to lambda over a. And as a result, we have alpha equals to 2 lambda over a. This formula is not to be used directly, but you should prove it every time. So as you see, the angular width depends on the wavelength of the light source and the width of the slit. Now let's determine the expression of the linear width of the central fringe. The linear width is L equals to 2 OM1. We have determined OM1 by using the trigonometric function tangent θ1 equals to OM1 over OI. And here it is. So OM1 equals to OI times tangent θ1. Now we know that tangent θ1 is equal to θ1 approximately, since θ1 is very small, which is equal to lambda over a. And the answer is d times lambda over a. but L is double OM1. So L equals 2 times lambda D over A. As you can notice, that the linear width also depends on the wavelength and the width of the slit. It also depends on the distance between the screen E and the slit. So if D increases, the linear width of the central fringe will increase, and when A decreases, L will increase. But alpha is independent of the distance D between the screen and the plane of the slit. So it will remain unchanged. Notice here, as we approach the screen to the slit, the linear width L will increase. So you can see the linear width is increasing. Please read carefully the course of the chapter in the school book. Always keep in mind the remark of document 5B, page 287. Solve the applications, applying your knowledge 1, 2, 3, 5, 6, and 9 from pages 287 to page 291, and solve the exercises numbers 14 and 19, pages 297 and 299. Good luck.